Okay, we are going to get started. Good morning. All right. So today we are going to start talking about second derivatives. I started kind of hinting at what this is in the previous class. Today we'll actually look formally at the concept of it. And then we'll do more stuff with finding maximum and minimum points. And then see how we can find inflection points, which are based off second derivatives. And we'll have time for at least one application of these ideas to kind of our business scenarios that we had been looking at before. Got to move this. All right. So last time we talked about power rule, sum rule, and constant rule are three big rules for derivatives that we will be using. There are more of these rules, but these are the ones that we will be limited to. Quick thing, our final exam. So I've booked the rooms and everything. So now official week 16, Monday, that's December the 13th in the evening. Very similar to how we did the midterm exam, except this one is a little bit longer, 2 hours instead of an hour and a half. If you want to do the exam in person here on campus, I have booked this room and the other room over there, so you can come, but you need to tell me. I have to print off that many exams. COVID regulations have to know who's coming and how many people, all that stuff. So if you want to do the exam in person, you don't have to do any scanning or selfies, so that's a little more convenient. But you do have to tell me, and I've just posted the post with all the details, and the sign up form is there as well. This one, week 15, final exam details in that thing. Okay. If you are not available to do this in person, then you're still welcome to do it online. If you do it online, it's all the same rules and everything as the midterm. Nothing changing there. Anyone have questions about final exam now? All right. Okay, so let's get on with today's material. Do you remember our process for, yeah, okay, tell me. First derivative, not right away. First derivative first, then, okay, set it equal to 0. Okay, solve for x or q in this case for that first derivative when it's equal to 0. Then check those points in the second derivative. So find first derivative, set to 0, solve for x, check in second derivative. That's our process. Go ahead. Find the second derivative and test these points in the second derivative. You guys have answers? Okay, tell me the turning points. 3 and 1, okay. And what are they? This is a max, and 3 is a, okay. Let's take a look and see if we get the same answers here. So our first derivative, total cost prime is equal to 2. So q squared minus 4q plus 3. Okay, so good review of all of those derivative rules that we were talking about. So first, sum rule, 4 different parts, just do the derivatives for each part separately, then just add them back up or subtract afterward. Second, we had our constant rule here. This is a constant, there's no variable in there, so that just turns into plus 0, so we don't bother writing it. And then our power rule, which we've been practicing a lot, we take the exponent, multiply that by the coefficients, and then subtract 1 from the exponent. Okay, so we set this equal to 0. So when TC prime is equal to 0, then 0 is equal to q squared minus 4q plus 3. And okay, so we're factoring it, and we are looking for lots of methods, but sum product is our kind of easiest way. First thing to check, do we have 2 numbers that add to -4 but multiply to +3? Okay, so -3, -1. They'll turn into 3 and 1 positive down here, but when we factor, we have to get our signs correct. So q minus 1, q minus 3. -1 times -3, +3. Okay, that works. -1 minus 3, -4. That works. So we have 2 possibilities here. Either q minus 1 is equal to 0, and therefore q is equal to 1, or q minus 3 is equal to 0, so q is equal to 3. So 2 possibilities. So we have 2 possible turning points because we can't guarantee for sure that they're turning points, probably, but we need our second derivative test here. So we'll do that. Total cost double prime. What is our second derivative? Okay, 2q minus 4. All right, pretty simple here. So, or pretty easy function. We can just substitute in these 2 q values here. So when q equals 1, our total cost double prime is 2 times 1 minus 4. That's -2, so less than 0. So at this point, our second derivative is less than 0. If it is less than 0, that means maximum point, as we have up here in the little legend at the top right corner. And then we do the same thing for, they have the graph. Okay, and then we have the other one for q equals 3. Total cost double prime, 2 times 3, 4. That's +2, so greater than 0. So that's a minimum point. All right, minimum. And maximum here. Okay, so this is a cubic. We have a cubed here. So the shape of this graph, we probably should have done this before we did the derivatives, but it could be color. We could have this shape. Sorry, wrong side here. This is positive, so this shape, or it could be hitting perfectly flat here for a moment, or it could just kind of have this pattern. So one of these three things, but we've discovered we have two of these turning points here, so it must be the first one. And we have a maximum point, a minimum point, and then the graph keeps going. Okay, so that's the process. Find the first derivative, set it to 0, solve for x, and then check in the second derivative.
Professor?
Yeah, question?
Yeah, I have a question. Can I ask?
Yeah.
Like when we were doing, finding the general kind of number, which is when it's added, it can multiplied, it can be +4, and then something like that. Can we use that formula, negative b plus minus?
Yeah. You can use, we're just solving a quadratic. You can solve it any way you want. Just sum product is very quick. If it's possible, then it's usually really quick to find the solution. So we just started with that. If we look at it for maybe 10, 20 seconds and we can't see a solution with that, then okay, move on to a more reliable general method. But the quadratic formula, the negative b plus minus square root, that thing, is very reliable, but it's slower. So that's why we started with some product. But any way you can solve your quadratics, that's totally fine.
Thank you, Professor.
Oh. All right, some review stuff, and then we'll get on with some more examples. So to remind you, this is the whole thing, the reason that, at least for now, we're talking about calculus. So a maximum of a total revenue curve like that, or the kind of most efficient minimum possible slope of a total cost curve like that. Those are those two very particular useful points that we are trying to find. Well, idea of derivative, we have a curved line. We are trying to find the slope at some point on that curved line. I won't repeat the whole process here, but that's just the idea. That's where all this is coming from. We talked about notation last time. And we have these 1, 2, 3, 4 ways of writing first derivative. We need to be familiar with, with all of those things. Those all mean the exact same thing. This one here, it's not a fraction. D is not a variable there. Just that whole thing together just means find the derivative. Rules are derivative rules. We reviewed this already in the example. As I said before, there are lots more of these rules. These are just kind of the early ones, but we can still accomplish a lot with these rules. Turning points, we talked about this as well. So what the derivatives are telling us about these turning points. So if we have a minimum point, then the slope at that minimum point is 0. It's flat, so slope is 0. So our first derivative should be equal to 0. Same thing for the maximum points here. And what we will really kind of properly talk about today is this second part with the second derivative. So this first function here, we have to check that second derivative and for the minimums and maximums because we don't want to be fooled with this situation where the graph does go flat, but it doesn't actually turn. It continues on in the same direction. And when that happens, the first and second derivative will be exactly 0. So we need to check to our second derivative test to know the type, and also so we know it's not that third type there. What else? A little bit more of this. Okay, we looked at this function here. We graphed this thing, and we did sort of our derivatives here, and we found out where our maximum and minimum points are. And then we talked about how the minimum point there and the maximum point there, if we line them up, the first derivative is exactly 0, because first derivative tells us the slope, and the slope is flat, so slope is 0. So first derivative should be exactly 0 at those points. And then also we talked about kind of these intervals. So in this middle interval here, for example, the original function is increasing. And for that whole block, the derivative is just positive, because positive slopes. So first derivative should be positive. And then same thing, decreasing here. So negative, decreasing here, negative. Okay, so that much is clear, that relationship? Yeah, okay. So when we add the second derivatives, things get a little more complicated, which we'll get to in a moment. Actually now. Okay, so let's do our whole turning points process again for this function and include your second derivative tests. Find the first derivative, set it to 0, solve for x, check in the second derivative. They shouldn't be too hard. Okay, what turning points did you find? Okay, so 9 and, okay, but something is happening at 0. Okay. 5. Okay, so let's see what we have here. We do have a quartic, something to the exponent 4, so it could be up to 3 turning points in theory. So let's see what we get here. First derivative, y prime is equal to 36 x squared minus 4x cubed. All right, and we set that equal to 0, so 0. 36x squared minus 4x cubed and okay, so common factor of 4x squared, and then inside our brackets, 9 minus x. So just in case any of you are tempted to say, well, common factor of 4x squared, so just divide and we're left with just 9x squared. Don't do that, because if we did that here, we would forget that x equal to 0 is one of the roots here. So we're just kind of factor it out, but don't eliminate it. So solutions here, 4x squared is equal to 0, so x is equal to 0, or 9 minus x is equal to 0, so x is equal to 9. So 0 and 9 turn out to be the 2. All right, so what types are these? What types are they? And that is our second derivative test here. So second derivative, y double prime is 72x minus 12x squared. Okay, so if we substitute in these points, when x is equal to 0, then, okay, the whole thing is just 0, 0. Okay, so second derivative will be equal to 0. When x is equal to 9, second derivative is 72 times 9 minus 12 times 9 squared. Is this negative? Okay, so negative number here. What I would notice here, the 72, that's 8 times 9, and then times 9 again, and then minus 12 times 9 times 9. So the second term is going to win there, and the result will be negative. We can see the actual number 36, but we really just care that it's going to be negative. Okay, so x equals 9. That is what kind? All right, so we have a maximum here. But what's happening when x is equal to 0? Okay, so it's going to go flat, but it's not actually going to turn. It's going to keep going in the same direction. So this is the graph here. It's going to look like this. And we can see when x equals 9, we have this maximum point here. Our slope is flat there. So that one's easy. But then we also have this other point here where x is equal to 0. This is our thing where the slope is going perfectly flat, but then continuing in the same direction. So this is our case. This is why we are doing our second derivative test, because we could have points like this, and we don't want to be sort of fooled into thinking we have an actual turning point. Okay. Yes, so based on this second derivative, we can say that this is not a turning point. Actually, we can say something a little better than this, give a little more detail. There is another name for this kind of point. This is basically what I was asking you in the preview question. Inflection points, yes. So that's the next thing. So inflection points, and those are coming from our second derivative. Okay. When we finished the last class, we looked at these, and I said the next thing that we're going to talk about is this, curving up and curving down. So so far, we had just been thinking, okay, well, where is it increasing and where is it decreasing? But we can also say, where is it curving up and where is it curving down? These shapes here. So if we add that from our second derivative, right, So this is what the second derivative of this function looks like. Okay, that's a little complicated. I told you it's, that's why I told you when we looked at this one, I said stare at this until it makes sense, because now we're adding this kind of extra layer to this. This is second derivative. This is all from second derivative. Yeah. Okay, so we're going to try to understand the relationships between these three things here. Just to remind you, the blue one is the original function, green one is the first derivative, red one is the second derivative. So the relationship between the original function and the first derivative, green and blue, we talked about that lots last time. We can see, and we reviewed that today as well. So maximum point 0, minimum point 0. We can see those things. We can also notice relationships between the first derivative and the second derivative, so the green one and the red one, because the red one is a derivative of the green one. So where the green one has this maximum points, the red one has a 0. Okay, so that part of the relationship is not too complicated, but it's the blue one and the red one that we care about. Just before I explain what's actually happening, 2 weeks ago when we looked at the first version of these graphs with x squared, I said something about intersection points. Does anyone remember?
Yeah.
What did I say about intersection points? Right, they don't matter, okay? So you might think, oh, well, something special is happening here. They're completely unimportant, so forget about them, okay? So don't get distracted by the intersection points. What we care about is always this kind of vertical relationship. If we draw a straight line, what's happening here versus here versus here, okay? So that's the thing that we care about. So let's actually talk about the blue one and the red one now. So the blue one here, we see this curving up pattern and this curving down pattern. So for this part of the graph, it's curving up, or we could think of it as like speeding up if we want to, if that helps. And then for the second half of the graph, we have this sort of curving down or slowing down kind of pattern. Okay. Where does it look like it changes? Okay, so where x is equal to 3, right about here, it seems like the pattern changes. Before this, it kind of looks like an x squared graph. And then after that, it looks like a negative x squared graph. Right, there's this flip between the two. And notice that flip is happening where we have a maximum point on our first derivative and a 0 on the second derivative. So that point of, repeat this here again. So if your second derivative is positive, if we look at all the areas where the function is curving up, then the red line here, second derivative, is positive. The y values are positive. All the areas where the blue one is curving down, the second derivative is negative for that whole interval. And then when it is exactly 0, that's where we have this inflection point, this changeover between the two. So that's our fancy new term here. Inflection point just means where we change between curving up to curving down or curving down to curving up, either direction. Yep. Yep. You're thinking slope. I was talking about the y values of it. Yeah. Yeah. So let's look at that again. So our this line in here. So on the left side of this line, the red value is positive. The y values are positive that whole time. When the red one is positive, the green one is increasing for that whole interval, and the blue one is curving up for that whole interval. And when the red one is negative, the green one, the first derivative, is decreasing for that whole interval, and the blue one is curving down for the whole interval. And then when the red one is 0, green one has a maximum, blue one has the inflection point. Yeah. Okay, so that's the relationship happening with all of these things. This there are more derivatives, third and fourth and fifth and whatever. They're almost never used. So if you can understand up to this level of depth with the second derivative and how it connects to the first or the original function, then that's most of it. Okay, so this final graph here, this one as well, keep staring at it until you can see these connections, especially between the blue one and the red one. All right, let's try that. So for this function here, please try to find the inflection points, turning points and inflection points. All right, do we have answers from anyone? Turning points? And inflection point? 20 for an inflection point? 10 for an inflection point? Okay, we'll check them. So first derivative here, y prime is equal to 6x minus 0.3x squared. That's equal to 0, 6x minus 0.3x squared And what would we do? 0.3x, okay. And 20 minus x here. Okay, so common factor there. And that means that I won't write out all the detail here. So if this one is 0, then 0.3 times x. So that just means x must be equal to 0. Or in the other one here, if it's 20 minus x, then x must be equal to 20. Okay, so we have 2 interesting points given our first derivative here. Second derivative, 6 minus 0.6x here. Okay, and we'll test these points. So if x is equal to 0, then our second derivative, excuse me, if we are substituting 0 in here, then the result is just going to be 6. So that's greater than 0. All right. And when x is equal to 20, second derivative will be equal to -6. And then that's less than 0 here. Okay. So at x equals 20, what do we have? Maximum points. And when x is equal to 0, we have a minimum point. Okay. We're not done though, because now we're looking for inflection points. So we'll take, I'm gonna need some space to draw. Okay. So our second derivative, we said is 6 minus 0.6x. Right, so we set this equal to 0. Second derivative, cleaner. Second derivative equal to 0. So 0 is equal to 6 minus 0.6x. And then x is equal to 10. Okay. So we have lots of information about this function here. Let's try to, let's think about what it would look like, and then let's see if that matches what we found with our derivatives here. So this is an x cubed. Our coefficient is negative. So what should the far right side of the graph do? All right, so right side will be decreasing, and our exponent is an odd number. So left side, all right, opposite direction, that's going to be increasing. It's a cubic. So as we said, we could have this, or this, or this, but 2 turning points here. So it has to be the first type. Yep. Exponent is odd. If the right side's going down, the left side must be going up. Okay, so we have this basic shape, and we know that we have a minimum point should be first and a maximum point should be second. Minimum at 0, then maximum at 20. So that order matches. Okay. That here. So we have this minimum at x equals 0. We have this maximum where x equals 20. And then we have this inflection point here, right here in the middle, where x equals 10. So we have the basic shape. We have 3 different kind of key points on this function, and we also know exactly where they are. We could just put these back into the original function and get kind of the y values of each of these if we wanted to. We'll skip that here, but that would be a very easy kind of extra step to do. Yeah. Not always. In 2 slides, I will explain that. So let's just look at this function here. And can you try to identify now visually how many intervals of curving up and curving down do we have? And then let's give everyone a moment to look. And how many inflection points then also? So take a moment and look, and then I'll ask you. It's from the second derivative. Okay. So I hear some people saying 3 up and 2 down, like up, change, down, change, up, change, down, change, up. Those are intervals of increase and decrease and turning points. That's the right answer, but to the wrong question. We're looking for curving up, curving down, and inflection. So look again. Take some more time to think. Turning points and inflection points are independent. Okay, so curving up, curving down, take another moment and look, and then tell me.
Two down.
Okay, so how many curving up do you see? Two. Okay, tell me where one of them is. Tell me where's the first one? From what x value to what x value?
From -2 to approximately -1 point.
To about 0. Okay, so here is a curving up interval. That whole time, it looks like a graph of y equals x squared. All right. Tell me another interval of curving up.
Around 1.
A 1. Okay, I'm gonna say it's a little past maybe 1.2 here or so, and then it stops at 2.
No, it goes up.
Goes up to infinity. Okay, so we have curving up to infinity on that side, and then curving down are then the other two between. So if we want the exact location, then we would have to kind of do our calculus tools. But so remember, curving up has this like y equals x squared sort of shape. Curving down has this negative x squared shape. So this part here, we can see this kind of U shape, and then we see this arch shape afterward. Around x equals 0, it's switching. Because that's an interval of increase. That's based on the first derivative. This is another layer based on the second derivative. You're thinking of first derivative and just slope increasing and slope decreasing. This curving up, it's like speeding up and slowing down. So like imagine if you're in a car and you're driving towards a red light. Okay, so your car is moving forward and then you start pressing the brakes. You're still moving forward, but you're slowing down. So your acceleration is negative, but your speed is still positive. So that's the kind of the different things happening here. Okay, so it takes some time to think about it to have it make sense, but it's independent of the first derivative, turning points, and intervals of increase and decrease. It's this curving up, this slowing down, speeding up, slowing down, speeding up like this. Okay. All right. So the other question that you had here, or sorry, based on this, how many inflection points do we see? 3, right? final thing here, just in between. That's an inflection point, that's an inflection point, and that's an inflection point in between each of these intervals here. Right? So types of inflection points. These are the three basic scenarios. We could have an inflection point, or most commonly, they would be here, right between two turning points. So there's like a maximum and then a minimum nearby, or we could have the reverse situation and it's a minimum and then a maximum nearby. So nearby turning points is one scenario. Second scenario, not that common in general, but when we look at these total cost curves, we will see it very often, is where there are no nearby turning points. Slope actually never gets to flat here, it just switches type. So this curving down here, curving up here. There could be other turning points later, like this, but if that happens, there would need to be another inflection point before that thing happens. So no nearby turning points. And the third type is kind of our special case where our slope goes exactly flat. And we've been talking about this case a few times already. Curving up, curving down, curving up like this. But our slope is going exactly flat at that point. So these are the three basic scenarios that we should be kind of looking out for. There is technically a fourth type where it's like a false inflection point and we use a third derivative to check for that, but we are not going to run into that in this class, so I'm just going to pretend that doesn't exist. These three are enough for us to be able to identify. Okay, good so far. All right, so, right, we'll get to an application in a moment. So this is just a summary of all the derivative stuff we've been talking about with these special points. So if we have a minimum point, then original function is flat, first derivative is 0, second derivative is positive, maximum flat, first derivative 0, second derivative negative. Inflection points, our original function is still increasing or still decreasing for the whole at that point. It could be either one. And first derivative is not 0, second derivative is 0. And then this kind of weird special case, function is flat and both derivatives are exactly 0. That's the summary of the points that we should be able to identify and what we use to identify them. Last bit about this before we get to more practice. Notation. So we talked about these 1, 2, 3, 4 types for first derivatives. Second derivatives, also lots of ways of writing them. So these two we've been seeing so far, and these aren't so bad. So y prime and y double prime, f prime of x, f double prime of x. The other two are a little weirder. The second derivative version of this thing is this. And we read it as d squared y over dx squared, but it's not actually an exponent. It's not actually a fraction. Just that whole thing just means second derivative. You just need to memorize that whole thing as a block there. And then the f of x version, similar, but just with f of x written out on the side. For every final exam, I have at least one question where I say, find d squared y over dx squared of this function. And it just means find the second derivative, but like half the students leave it blank because they forget about this thing and they forget about this notation. Again, we don't need this too much for our class, but when you do later calculus stuff, this notation becomes essential for multivariable, like 3-dimensional calculus stuff. So I'm introducing it to you here. Other textbooks, other professors will use this and expect you to know what it is. So learn that one too. Questions? So let's finally get to some of our applications here. So let's say we have this scenario and we want to find a maximum total revenue. Maximum total revenue. So if we need that, we should find the total revenue. We should have our total revenue function, but we haven't been given that. We've just been given a demand function. So here's a relationship between P and Q. What is P? What is Q? Okay, P is price, Q is quantity sold specifically. So not manufactured, not shipped, specifically quantity sold. Okay, so here's the relationship between price and how much we're going to sell. It makes sense that there's a relationship. Higher price, fewer people will want to buy it, so you sell fewer things. Okay, so let's try to make an equation here for total revenue for this scenario. What is our basic equation for? Right, price times quantity, P times Q. How can we use this thing to make an equation? Right, so that's P. Right, we just substitute that in for P here. So 50 minus 2Q times Q. So 50Q minus 2Q squared. Okay, so negative something Q squared. We know that we're going to have basically this kind of shape. We're asked to find a maximum. Okay, we have our derivative tools. It seems all possible here. But before we get to that, the question is also asking us to find MR. Not M, it's not maximum here, it's something else.
Marginal revenue.
Marginal.
Okay,
revenue.
marginal. So MR is MR, marginal revenue. And we can have MC for marginal costs. We'll see in later questions. Okay, can someone explain the concept? What is marginal revenue?
The profit revenue coming from each product.
Sorry, can you say that again?
The revenue coming from each product.
Close. I want a little more detail.
From each additional unit sold.
Okay, from each additional one. So let's say I sell 100 units. Okay, so here is my Q at 100. Okay, and also we could figure out here is my total revenue for that when we sell 100 units. Okay, then marginal revenue, I'm asking here, what if I sell one more? What if I sell 101 units? Then if we do that, then we'll have some other Q equals 101, and we'll have some other total revenue, this one at 100, this one at 101. What's the difference? If I sell one more unit, how much extra revenue do I get? That's marginal. Okay, so marginal means kind of at the limit. That one more step for Q, how much more extra money do we get? Oh, our total revenue would go up by $50. Okay, the marginal revenue is 50 for that point. Marginal revenue is going to keep changing at each point for this function. So if we sell one more thing, how much extra money do we earn? Or it could be less as well. Okay, so it's the difference between these 2 points. If we say that our Q here, it's the kind of change in Q. And then we're asking, what's the change in total revenue? Does that kind of look familiar? Like what? Slope. Okay, so the mathematical relationship of slope perfectly matches our practical definition of marginal revenue. So the marginal revenue is the slope of the original function, because the slope says if x goes up by 1, how much does y go up or down by? And marginal revenue is also exactly that thing. Do we have a way of creating a function that tells us the slopes of some original function? What? Derivative. Okay, so the really key thing here, marginal revenue is equal to the derivative of the total revenue. Again, the practical definition of what a marginal whatever is perfectly matches our definition of what a derivative is. So we use this tool all the time to talk about marginal whatever. Economists are always talking about marginal benefit, marginal whatever, at the very limit of whatever thing. That's all calculated with derivatives. Okay, so marginal revenue is equal to the derivative of total revenue. And our total revenue in this case is 50q minus 2q squared. So that is 50 minus 4q. Yes, by definition, yes, absolutely all the time. And derivative of total cost is marginal cost, and for whatever marginal or whatever thing you're measuring, marginal of that thing is just the derivative of that. So yes, this is a really fundamental relationship in economics used. This is why calculus is such a huge part of everything in economics. Okay, so our maximum point process here, we do the same thing that we've been doing before. And we just set this equal to 0. So where our marginal revenue is 0. So where selling one more thing doesn't earn us any extra money, that's going to be this maximum point here. So then 0 is equal to 50 minus 4q. And q is equal to? Yes, which is? 12.5. So q is equal to 12.5 at that maximum. Yes. Okay. So okay, so we can see our maximum points here, and if we draw our line down, it seems like it hits, and the green one is our derivative. I should have written this in green here instead of red, but where our first derivative hits the x-axis here, that's exactly at this point 12.5. That's where it's 0. That's where we have this maximum. We're not quite finished because the question didn't ask us where is the maximum revenue. They want the actual dollar value of the maximum. Right. Okay. So we take this 12.5, that's the location of the maximum, and we just put it back into our total revenue. So where Q is equal to 12.5, then total revenue is 50 times 12.5 minus 12.5 squared. And what is that? If you want. Mm-hmm. Three 12.5, and then the solution to that also 312.5. You might notice that this number here is exactly double this one. It's a symmetric function, so those things probably should happen, but good to do, kind of work out the math anyways, and make sure that's going to happen. So there we go. We've found the location of our maximum and then the actual value of the maximum. Okay. All right. So any questions about the example? We're good. All right. We'll have lots more of these, and we'll come back to these scenarios with our cubics and adding total cost and then making profit and all of this. So this is just kind of our simple derivative tool so far, finding a maximum point, but we'll add in kind of the inflection points in a bit. All right. Did have more of these, but the other classes didn't get there. So we'll come back to that later. Right, so notation, these 4 different ways of writing each of them, you just got to remember them. Again, in class, I'll mostly be using the first 2, but you need to be able to recognize all of them. This function, this graph here, just again, stare at this until it starts making sense. There's a little bit that I forgot to mention with you guys, which I'll just kind of help explain here briefly. Looking at the original function, the blue one, so this whole idea of curving up, let's look at kind of a whole bunch of points on this original function. At the start here, the slopes are very negative, right? And then the slope is still negative, but less negative. It's getting closer to 0, and then less negative, closer to 0, hits exactly 0, and then it's slightly positive, and then more positive. So the whole time it's getting closer to positive infinity. That's kind of our math definition of this curving up idea. Closer to positive infinity. And then on the other side, positive, but then less positive, exactly 0, slightly negative, more negative, really negative, closer to negative infinity. That's what's happening with this curving down relationship. So that's kind of something that can help you recognize what's happening here. There was one term I skipped over. Okay. All right. Forgot to mention a few things. Formally, any other math textbook or whatever, instead of saying curving up, they will say concave up and concave down. Those are the more standard terms. I just think curving up, curving down are a little easier to understand, so I've been using that. But any other book or professor will use these concave up, concave down words, so might be good to just kind of remember those. Okay, I think that was all I wanted to say. All right, So lots more applications of derivatives to our business scenarios. And then that's kind of the final thing that we'll do. That'll take us to the end of next week. Anyone have questions before we wrap up? Okay, so fun with second derivatives. That's now hopefully we have a basic understanding of that. Lots more applications in the following classes. And I will, that's it. I'll see you guys on Thursday.